Welcome to EDU World Space.
This three-part question starts by asking us to sketch a diagram that shows the definition of the crystal field splitting energy for an octahedral crystal field. This is just how these d orbitals separate in an octahedral complex. And the way they do this is by splitting into a set of 2 higher energy orbitals and 3 lower energy orbitals. These higher energy orbitals are the dx squared minus y squared and the dz squared. The lower energy orbitals are the dxy, the dxz, and the dyz. The difference between this higher energy orbital and the lower energy orbital is shown by a delta. And this leads us to part B, which asks us the relationship between the magnitude of delta and the energy of the dd transition for a D1 complex, where this magnitude, or this delta, is equal. So delta is equal to the energy of a dd transition. And that's in a D1 complex. Part C then asks us to calculate delta in kilojoules per mole for a complex that has an absorbance maximum of 545 nanometers. And to solve this problem, you need to know the equation E equals hc over lambda, where h is Planck's constant at 6.626 times 10 to the minus 34 joule seconds. C is the speed of light at 3 times 10 to the 8 meters per second, and then lambda is your wavelength. So if we write this out with all of our values, we'll have h as 6.626 times 10 to the negative 34 joule seconds. C of 3 times 10 to the 8th meters per second. And then our lambda, which is 545 nanometers, but I'm going to go ahead and convert that to meters. So we have 545 times 10 to the minus 9 meters. So our meters cancel and our seconds cancel. This gives us 3.65 times 10 to the minus 19 joules. And then we're going to convert that to kilojoules. So we have 1 kilojoule for every 1,000 joules. And then we're also going to multiply it by Avogadro's number to get kilojoules per mole. So that's 6.022 times 10 to the 23rd. And the answer to that is approximately, or rounded to 220 kilojoules per mole.